Hello and welcome to Los Alamos National Laboratory's Math and Science Academy. This video is one of several in which we will explore the Common Core standards for mathematics as they relate to teaching about rational numbers. We will be looking at rational numbers through two lenses. First, the sequential trajectory of how we bring in the simple concepts early in the students' learning in third grade and move through fourth, fifth, sixth, seventh, and ultimately eighth grade to expand into irrational numbers. The other lens that we'll look at is through the Common Core's standards for mathematical practice, which are listed here. In each video, we'll be focusing on one or more of these mathematical practices. Finally, in each video, we will be looking at the ideas presented through the lens of something we call IC Flip. IC Flip is an acronym for the way that students begin to see and understand ideas, first starting with the concrete and moving up to the very abstract and procedural. We'll start out with images, which give the student an opportunity to see something in real life that they can connect to. Use that to illustrate a concept. As we get a little bit more abstract, we will bring in some facts and language that will help the students talk about the problem or the idea at hand. And finally, towards the end of the progression, we will look at procedures which are strictly abstract using symbols and are, generally speaking, the most efficient ways, but the most abstract and difficult to understand. In this video, we will be discussing standard 4.nf.c.5, which is about decimal fractions, and it's really a lead-in to decimals in general, so we're beginning to move toward that. The mathematical practice that we'll be looking at is number 6, attending to precision. Let's take a look at this standard in a little more detail. It's part of 4.nf, which is about extending students' understanding of fraction equivalence and ordering. The C section of this is about decimal notation for fractions and comparing decimal fractions. So we'll introduce this term. And dot 5 is about expressing fractions with denominators 10 as an equivalent fraction with denominator 100. And then we'll use this technique to do some simple combinations. We're not going to get into decimal notation yet, but we're going to be working with the precursors to that to set the stage for working with decimal notation by working with these decimal fractions. The standard that we'll look at in this video is SMP.6, which is attending to precision. The learning goals for this standard are first to understand the term decimal fractions and begin to be fluent in how they work. Secondly, to understand the equivalence of decimal fractions that have different denominators. Third, to add and subtract decimal fractions, including those that are larger than 1, which will bring us to reviewing and working with mixed numbers. And finally, we want students to begin to recognize numbers as tools for measurement with various levels of precision. In other words, that numbers are no longer counting things, but can be made up of a sum of whole parts plus fractional parts, specifically decimal fraction parts, to represent different levels of precision. We'll begin with this problem, which is to use base 10 materials to show that 4/10 and 40/100 are equivalent. And then we'll continue using the same materials to find 4/10 plus 7/100. The solution we're going to use here is using base 10 blocks. They're pretty common manipulatives found in classrooms. And when we use them, 1 square represents 1 unit. So this is 1 unit. And if we want to look at 4/10, we're going to explore 4/10. We need to break this 1 unit up into 10 parts to generate tenths. So each of these vertical bars represents a tenth. And 4 of them would be represented by shading 4 of these. And numerically, that's this 4/10. Now, to look at the equivalence with 40/100, we'll take another 1 block, and this time, since we're working with 100ths, we need to break it into 100 parts. So each of these little squares is a 100th, and what you'll notice is that 1/10, one of these vertical bars, is represented by 10 100ths. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares in each of the bars. And that allows us to see the equivalence. If we're going to look at 40 100ths, well, here's 10 of them, 20, 30, 40, so here's 40 100ths. And just by looking at the amount of the unit that's shaded, we see that these two are equivalent. So 4 tenths is equal to 40 100ths. And students hopefully will also recognize how these numeric symbols relate, and how what we've done is just added a 0 on the end of the numerator and the denominator, which is the same as multiplying the numerator and the denominator by 10. We have 10 times as many hundredths as we do tenths, and so the same thing with the numerator. So now let's look at how we would then use these ideas to calculate a sum. We'll start with 4 tenths, which looks like this, and now some arbitrary number of hundredths. We'll pick 7, so here's 7 100ths. And hopefully what the students will recognize, and what you want to point out, is that we can't really add together these different units. We're getting towards the idea of common denominators for addition and subtraction, although that will come quite a bit later. But we can't add these bars and these little squares. They're different things. They're different units. And so in order to do that, we want to convert, and that's why we discussed this equivalence, we want to convert the tenths into 100ths and look at 4 tenths as 40 100ths. And now we have all a bunch of 100ths. Everything's the same, and we can add them together because we just have 47 of these hundredths. So 4 tenths plus 7 hundredths is 47 hundredths. And as I said, this is getting toward the idea of needing a common denominator. But right now we're just understanding units have to be the same to add them together. So our takeaways is, first of all, that it's easy to convert tenths to hundredths. We just have to multiply by 10, and we'll have 10 times as many hundredths as tenths. And that fractions, in order to add them together, they have to have the same units, the same denominator. Next, we'll look at the problem that was specified in the standard. Express 3 tenths using a denominator of 100, and then using your result, find the value of 3 tenths plus 4 100ths. This time, we're going to use a metric ruler, a different lens, which will bring some more understanding of measurement and some additional language as we get through this. So we begin with a metric ruler. This is the metric side of a 6-inch ruler, and so students may actually be able to use one of these physically and see this. And to understand 3 tenths, we first need to define a unit. What should a unit be? And for the purposes of this, it's easiest to use one unit being defined as 1/10 of a meter, a decimeter. So this is the first piece of language that students might not understand and need to be introduced to. That's a decimeter, is 1/10 of a meter. And within this, then, 1/10 of this distance is 1 centimeter. Okay, a centimeter, which is 1/100th of the whole meter, right? But our unit is a decimeter, so a centimeter is going to be represented as a tenth. There are 10 of these centimeters in the decimeter. So now we can express 3 tenths by 3 of these centimeters. 3 tenths is the amount you get when you shade 3 of these tenths, and that's 3 centimeters, okay, since a tenth of a decimeter, which is our unit, is a centimeter once again. So now we want to express this using a denominator of 100. We're going to need to look a little deeper here and zoom in on this. Here's a tenth here. So if this is a tenth of our decimeter, then 100th is a tenth of that, which is a millimeter. So our hundredth unit now is 1 millimeter. So 3 centimeters is 30 millimeters, right? These are millimeters, hundredths are millimeters, so 3 tenths is the same as 30 100ths. And that's the way we express 3/10 using the denominator of 100. And once again, students may see that symbolically, or you might want to point out symbolically, that what we've done is multiplied the numerator by 10. We have 10 times as many of parts that are 10 times smaller. The hundredths are 10 times smaller than the tenths, and so we multiply the numerator by 10, making 10 times as many of them, and we get the same overall amount. Looking at this is, of course, more procedural and moving into very abstract symbols, so it's also important that they understand this from a visual level. So next, we will add our 4 100ths. Well, here's 4 100ths. Remember, a hundredth is a millimeter, so 4 of them is this much. And we can represent the sum by looking at the total distance, which is 34. Here's 30 plus 4 hundredths, and get a number 34 hundredths. So abstractly, this problem is very similar to the previous one, but we've put it in a different context, and that is of a metric ruler, and we've done that for a number of reasons. Our takeaways for this slide are first to connect students with the idea of decimals. They haven't quite gotten there yet, but these sums of fractions with denominators that are powers of 10 are the basis for our decimal system. Also, to begin to look at numbers instead of as counting things, as measuring things, which brings up the idea of precision. So we use this metric ruler to draw that connection. There's some language in this slide. The first word, decimeter, which represents 1/10 of a meter, and more generically, the prefix deci, which represents 1/10, and is in fact the prefix of the term decimal and our decimal system. The term centimeter, which is 1/100th of a meter, and the prefix that goes along with this is centi, which is 1/100th, and students can remember this from the term cent, which is like a penny, is 1/100th of a dollar. And the word millimeter, whose prefix milli represents 1/1000th. There are also corresponding prefixes, deca, centa, and milla, which represent the whole numbers 10, 100, and 1000, as in, for example, decade for 10, centipede for an animal with 100 legs, and milla, as in like millennium, for 1,000 years. I should point out that milla is particularly prone to confusion, as it might be confused with the word million when it's actually related to the number 1,000. These are good prefixes for students to understand, as they'll show up in a lot of places in their reading, not just in mathematics. The other idea here is that when we take units and break them into smaller and smaller parts, we're able to measure entities with more and more precision. This idea of numbers having precision and not just being counting things is inherent to a more sophisticated understanding of numbers. It's also part of the standard for mathematical practice number 6, understanding numbers as more than just counting things, but having a precision associated with them. Next, we'll look at a problem that involves many of the same ideas, but also introduces mixed numbers and some subtraction. Here's the question. Ali is knitting a scarf that will be 2 meters long. So far, she has knitted 1 2/10 meters. How many more meters does Ali need to knit to complete the scarf? And then we'll do some unit conversion and ask how many more centimeters does Ali need to knit. So we're looking for a 2 meter long scarf, and we'll use a solution that visualizes this with meter sticks, going back to our images. Here's a single meter, and for 2 meters we'll put another one next to it. Since we're going to be looking at tenths of meters, 1 2/10, it will be helpful to break this into our tenths and figure out what's a tenth of a meter. So we break the meter into parts, each of which is 10 centimeters, and that way we'll get 10 parts across the whole meter. In other words, 1/10 of a meter is 10 centimeters. And now we can start to look at the problem given our scale. We've got our scale all set up and defined our units. So 1 2/10, well, here's 2/10. If this is 1/10, then this distance is 2/10, and the amount of scarf that we've already knit would be represented by this distance. And what we're after now is how much more scarf do we need to knit. And this is kind of a subtraction problem because, well, it is a subtraction problem because what we're doing is we know we need to get to a total and we have part of it, and so we need to subtract how much we've already done to get how much is left to do. Now in this particular case, we want to work in tenths, and so we know that this meter is incomplete, and it will help us to recognize that 1 meter is 10/10 of a meter. So this meter is 10/10 long, and so the question is 2/10 of a meter plus how much more do we need to get to 10/10 of a meter? And this is a straightforward subtraction problem now that we have, again, the same units. We're working in tenths of meters. The answer is 8/10 because we know that 8 plus 2 gives me 10. And we know that we have 8/10 of a meter left to knit. So this is our answer to the first problem. Ali has 8/10 of a meter of scarf left to knit. And if we want to convert that to centimeters, we have to remember that 1/10 of a meter is 10 centimeters, right? We had that before. 1/10 of a meter is 10 centimeters. So 8/10 of a meter is going to be 8 times that. And so she needs to knit 8 times 10 centimeters or 80 centimeters more. Our takeaways here are pretty similar to the previous ones. First, though, we've introduced mixed numbers. And in order to work with them, we want to express the wholes as units of the fractional part. In other words, the whole number here, the 1, we want to work with that as 10/10, and that allows us to do these manipulations, in this case subtraction. Once more, we're moving towards that idea of a common denominator, which we'll come up to later with the procedure, but really understanding here why we need to do that. The principle behind that is that 1 whole is equal to 10/10, or as we saw in the previous 100 100ths, and more generally that 1 can be written as any number over itself, but of course here we're focusing on denominators that are powers of 10. We also want to reinforce or introduce the idea that how many more, that language is often related to a subtraction problem. We'll finish off with this problem expressing 47/100ths as a sum of tenths and hundredths, and expressing 247/100ths as a sum of whole numbers, tenths and hundredths, to really emphasize the breakdown of numbers into their decimal parts, if you will. And we will introduce the term decimal fractions to help students make that transition from fractional notation to decimal notation. We're going to use number bonds here, which is a more abstract idea than what we've seen so far, but really helps students to understand this idea. Our number 47/100ths, we'll begin by looking at it as 47/100ths, and we're going to break it into 2 chunks, and the chunks are going to be 40/100ths and 7/100ths. This is very much along the lines of what students have done with place values in whole numbers, breaking the number 47 into 40 plus 7, or 4 tens plus 7 ones. But now we're looking at 47/100ths, and so we have 40/100ths and 7/100ths. And then with the previous equivalences that we've seen, students may hopefully recognize 40/100ths as 4 tenths. So we're breaking that down in reverse from hundredths to tenths. And you'll recognize the idea of reducing fractions, or removing. All we did was remove the zeros from the numerator and the denominator, the ending zeros. And now we have the idea that 47/100ths can be made up of some tenths and some hundredths, 4 tenths and 7/100ths, and we get our solution. We can take this one step further with the number 247/100ths. We're going to do the same thing, except now we have 3 place values in the numerator, a 200, a 40, and a 7. And like we did with whole numbers again, we'll break the numerators into 200 plus 40 plus 7, all of which are hundredths. So now we'll look at this, and as we did over here before, we can take the 40 100ths and change it to 4 tenths. So now we have tenths and hundredths. But what about this 200 100ths? Well, we know that if 100 100ths is the whole, then 200 100ths is 2 wholes. Now we've made the leap from fractions into whole numbers, and we have, as a sum, 247 hundredths is 2 wholes, that's the 200 hundredths, plus 4 tenths, plus 7 100ths. And hopefully you'll recognize this as starting to get very close to the idea of the notation 2.47. We can also then look at this as 2 and 47 100ths as a mixed number, because we have our whole number and then the fractional part. So we have some takeaways here. First, to be thinking of numbers as a sum of other numbers that have different levels of precision, and specifically thinking of them as the sum of fractions which have powers of 10 as their denominators. And we have a special name for those fractions. They're called decimal fractions. You know, they're very connected to the decimal notation where we use a decimal point. But a decimal fraction is a fraction whose denominator is a power of 10. And when we break fractions into sums of decimal fractions and whole numbers, we're right on the cusp of using decimal notation, which is coming up next. Again, this connects to the standard for mathematical practice about precision, because as we add these decimal fractions with larger and larger denominators, we're adding smaller and smaller amounts and making the number more and more precise. We'll finish up by looking at some mathematical writing based on the same problem that we looked at before about Ali knitting a scarf that's going to be 2 meters long. She has 1 2/10 meters completed, and we're asking the question how much more she needs to knit, both in centimeters and meters. We'll look at this mathematical writing. Initially, the student has solution A here, and you'll see a nicely drawn, what looks very much like a number line, and does correlate exactly with a number line eventually. The whole is left as a whole, and they break the second meter into tenths in order to represent the 2 tenths, and then just using these arrows indicate that what's left to go is 8 tenths, which can be done just by counting. It could also be done by taking the 10 tenths and subtracting the 2 tenths, which are complete, to get the 8 tenths. But either way, they come up with the result that 1 2/10 plus 8 tenths equals 2, which results in the solution. Ali needs to knit 8 tenths more meters, which we see pictorially here. When they move on to centimeters, they're really just doing a conversion of the 8 tenths by starting with a representation of this part of the number line here, 0 tenths, here's half or 5 tenths, 8 tenths, and 1 meter. So here's the meter, and they break it into the tenths as they need them. And recognize that 0, of course, is 0, and that 1 meter is 100 centimeter. Here's the equivalence right here. So 8 tenths, which is at the same location as here, would be 80 centimeters. So this is just a pictorial way of recognizing the relationship between the centimeters on the bottom and the tenths of a meter on the top. And so the conclusion is that Ali needs to knit 80 more centimeters. The second solution that's shown here is somewhat more procedural. They just take 1 2/10 and know that they need to complete up to 2 meters. So they take 2 minus 1 2/10, break the 2 down into 1 10/10. This is a number bond idea, which we spoke about some before. It's the reverse direction from what we did, but we can take a whole number 2 and break it into one whole and another whole, which is broken into 10/10. That allows us to take this whole from this whole and 2/10 from 10/10, leaving 8/10. So that's a more procedural way to do it, fairly abstract, but gets you to the right answer. And then with regard to the conversion to centimeters, they're just making the same kind of connection that we made before, which is that 1/10 of a meter is 10 centimeters, so 8/10 of a meter is 80 centimeters. There are not a lot of words in this writing. This is much more of a symbolic way of showing student writing, but the ideas are very clear, particularly in this one. Here it's a bit more abstract, but clearly the student got the right answer, and this is what we would be looking for further along when we're getting closer to the procedural approach. One more note about the standard for mathematical practice number 6 and precision. You'll see here what is becoming very close to a number line that is going to eventually have decimals. Here's 0, here's 1. This will be 1.1, 1.2, 1.5, and ultimately 2 as we think about decimal notation for all of this. So by this point, all of the ideas that we'd talked about with regard to decimal fractions are solidified well enough to jump on to decimal notations.